My name is Jung-woo, and I am a second-year PhD student at UCSD. Today, I'm going to talk about RoVISQ. This is joint work with my colleague Mojan Jara Haripi from UCSD and Seira Hitano from KDDI Research, and my advisor Finance Koshamper from UCSD. Okay, so video content accounts for more than 80% of the internet traffic. In particular, video traffic has experienced an even higher growth with the advent of streaming services. For example, there are remote vehicle control and metaverse. Recent developments in deep learning also have given rise to various video analytics, such as healthcare diagnosis. However, video data requires a large amount of internet bandwidth. It can affect the backend user's quality of experience. In order to maximize the quality of experience, video compression is a key enabler for the aforesaid applications. Sorry for my mistake. However, the video data requires a large amount of internet bandwidth. It can affect the backend user's quality of experience. In order to maximize the quality of experience, video compression is a key enabler for the aforesaid applications. So how video compression works? Video compression employs rate distortion optimization to adapt to different bandwidth constraints. As shown in this figure, when the user has high bandwidth, the video compression chooses an appropriate rate distortion model that can encode the video with higher video quality. Recently, deep learning-based video compression achieves impressive results by replacing all the components in the standard video codecs with deep neural networks. It has been explored by moving picture expert groups for adoption in the next generation video codecs. Unfortunately, DNNs have been known to be susceptible to adversarial examples. So small perturbation added to the inputs of a DNN cause it to misclassify the perturb inputs. Here is an example of adversarial attacks. So if we add a very small perturbations, deep learning-based classifier recognizes the video as a wrong class with very high confidence. Our paper focuses on deep learning-based video compression systems. However, the vulnerability of video compression has not been studied yet. So I'm going to talk about several motivations for our paper. First of all, compression techniques have been employed to remove the adversarial effect in several works. We also show that deep learning-based video compression can easily remove these adversarial examples. The robustness of video compression against adversarial perturbations remain largely unknown. So can the video compression be vulnerable to adversarial examples? So we want to find the answer for this question. Secondly, deep learning-based video compression models have a fixed rate distortion relationship through offline training. So each trained model has different rate distortion trade-off as shown in this figure. So here is a question. How adversary attacks affect these models? Can we only target the distortion or bit rate, or can we target both of them together? In this paper, we propose 3 new types of adversarial attacks. First, our bandwidth attack can increase the bit rate while maintaining the distortion. Second, our video quality attack can increase the distortion at a given bitrate level. Finally, our RD attack can increase both the bitrate and the distortion. So we will show how to realize those attacks in the later slide. The third motivation is that all of the adversarial attacks on video classification didn't consider video compression in their threat model. Here we modify the conventional threat model by targeting towards front-end video sources such as camera and also effect of downstream video classification system. So our goal is to find a compression-robust attack. We carefully craft an optimization problem that generates perturbations that are robust to video coding. Finally, we have a new design challenge. Video compression uses temporal coding structure to remove temporal redundancy between neighboring frames. To do this, Video compression groups a series of frames into sequences called group of pictures GOP to allow backend user to access video streams at any time. Typically, 3 types of GOP structures are used in DNN-based video compression systems. According to the GOP structure, the display and coding orders are different. So we should design our attack methodology to be robust to temporal coding structure even when adversary has no knowledge about the GOP structure. We systematically analyze our attacks on 3 GOP structures used in state-of-the-art video compression systems. Here are our contributions. We performed the first systematic study of adversarial attacks on deep learning-based video compression and downstream video recognition system. Secondly, we proposed 4 new adversarial attacks that result in high impact security. Thirdly, we construct a well-designed universal perturbation that is invariant to underlying DNA model, encoding parameters, and input videos. Finally, we showed the resiliency of our attacks against various defense techniques. So I'm going to present our threat model. We assume that adversary adds very small perturbations to a stored video to subvert the video compression over a long period of time. The figure shows the difference between the raw input video and perturbed input video. As we can see, our perturbations for the input video have extremely similar noise magnitude that remains stealthy to human eye. Here we consider 2 attack scenarios, which are offline and online attacks. Offline attacks use sample-wise perturbations that are independently added to each sample. In contrast, online attacks use well-crafted universal perturbations that can be used to attack at any video sequences at any time step. This is because the real-time constraints of the online attack prohibit the adversary from customizing the inject noise. Our adversary score is to selectively degrade the bitrate or distortion level compared to original rate-distortion relationship. We introduced 4 types of attacks, which are video quality attack, bandwidth attack, RD attack, and video classification attack. So video quality attack as unwanted distortion to invoke denial of service. Bandwidth attack causes buffering when user downloads the video. RD attack makes users to suffer from low quality or denial of service. Video classification attack suffers the model to misclassify the class. So here is our adversary's capability and knowledge. In offline scenario, we assume the adversary knows every encoding parameters, including compression rate and GOP structure. Second, since video coding standards are publicly available, we assume the attacker has white box access to open source model. Third, our perturbations are independently added to each sample because the attack latency is not constrained. In online attack, we assume that our adversary doesn't know any encoding parameters. For considering the challenging scenario, we also consider black box setting about DNN models. In black box attack, our adversary used a surrogate open source video compression model to transfer the perturbations to unseen systems. Finally, we assume that our adversary is capable of injecting perturbations onto real-time video stream by manning the middle attack schemes. Now let's move to our offline attack construction. In offline attack scenario, the raw frames are stored in the storage device. The victim wants to encode the video sequences using video compression in order to reduce the large amount of data. Before compressing the videos, our adversary will add small perturbations to the raw video so that adversarial perturbations are imperceptible to naked eye. This example shows that the perturbed input frames are generated. We iteratively add the perturbations to the input frames, and at the first iteration, we set a perturbation tensor filled with color value yellow. Then video compression starts working to encode the video data. Video compression first groups a series of input frames into GOP. Video compression uses temporal coding structure depending on the GOP structure. And so we use deterministic function to rearrange the frame orders. So for a given case, the nth coding order in the GOP is mapped to a new time step t using a deterministic function M. Finally, the victim encodes the perturb input frames with the deep learning-based video compression. We quantify the performance of the victim video compression based on two important measures, bitrate and distortion. By the characteristics of the temporal coding structure, video compression constructs a chain of dependency between all adjacent frames in each GOP. So we formulate the QoE factors for each GOP from the bitrate and the distortion measure with average function. Now we can generate the perturbations by maximizing the following loss function here. This loss function includes three different types of attacks by the value of xi. Xi equals to 0 means the video quality attack, xi equals to 1 is the bandwidth attack, and xi equal to 2 is the RD attack. We carefully constrain two QoE factors to successfully achieve the adversary goals. And then next, we formulate the adversarial loss for downstream video classification. In the loss function, we consider two types of attacks, untargeted attack and targeted attack. After formulating our optimization functions, we integrate all the loss functions to simultaneously derive perturbations on video compression and classification systems. There, we can generate sample-wise perturbations that are independently added to each sample. Now let's move to our online attack construction. Online attack is particularly challenging for several reasons. Firstly, the video compression is conditioned on the compression rate. Since compression rate is determined by the end user's network traffic, it is difficult for the adversary to infer the compression rate in real time. Secondly, the display and coding orders vary according to the GOP structure. So it is also difficult for adversary to know which GOP structure is using. Thirdly, the adversary may not be able to align image perturbations with the video sequence, which is also called boundary effect. Finally, the data distribution of the captured video is very dynamic. For example, some of the contents may have fast-moving objects or slow-moving objects. In order to tackle down the challenges, we train our universal perturbations that are agnostic to conversion rate, GOP structure, and input, which is stood for online attack. When we train the universal perturbation, we average the loss values across all training videos available to the attacker. For more details, please refer to our algorithm in the paper. After finishing training our universal perturbations, we inject the perturbations to the live video streaming by man-in-the-middle schemes. Now I'm going to talk about our attack performance. To evaluate our offline and online attacks, we construct two Gaussian noises for baselines. Here, the Gaussian noise case 2 has 2 times higher noise power than our attack. As we can see in this figure, our attacks can break the Rate-Distortion model of pre-trained video encoder by a large margin. We further studied the black box attack scenario. In this setting, we show that our universal perturbations trained on a surrogate open source video compression model are transferable to unseen systems such as conventional video codecs and unseen DNN models. This figure shows the white box attack performance on video classification. We evaluate the success rate and provide comparison with the state-of-the-art attacks on video classification. As we can see, our attack constantly achieves the highest success rate. In particular, we obtain over 90% success rate on the UCF 101 and gesture datasets. For our black box attacks on video classification, the proposed adversarial perturbations are also successfully transferred to unseen video classification models. And we comprehensively evaluate different defense mechanisms against our attacks. There are very few defense available for adversarial attacks on video domain. So we implement new defense mechanisms that rely on signal transformation to remove adversarial perturbations. We choose adversarial training, video denoising, and JPEG image compression to measure our attack success performance. Here we visualize some results. We show how our perturbations are robust against defense techniques. As we can see, our bandwidth attack can maintain the same image quality compared to original image, but it increased the bitrate over 80%. We can also see that the video quality attack keeps the bitrate constant, but adds several noise-like artifacts. Our RD attack generates a large amount of distortion as well as increasing the bitrate. We see that the defense technique cannot prevent our attack. This is because even if the defense techniques denoise the perturbed input, the error is still propagated from the perturbed input to the compressed video. So more experimental results can be found in our paper. In conclusion, so we present the first systematic study on our adversarial text to deep learning-based video compression systems. Our compressible experiments show that our attacks outperform on noise baselines previously proposed attacks in both offline and online settings. Furthermore, our attacks still maintain high attack success rate in the presence of various defense. And our video demo is available at this link. And thank you very much for attending this presentation. And please ask me the question if you have.
Thank you for your presentation. I have one question. Have you ever attacks against classical video compression algorithms? What I mean is like, is the issue in this case the fragility of deep learning models, or you just add so much information to initial videos so no compressed algorithm can process it adequately?
Sorry, can you explain once again?
Okay. Have you evaluated your attack against classical non-deep learning video compression algorithms?
So, yeah, we are targeting the deep learning-based video compression, and that has not been really easy. What you were saying about?
If I apply your attack, then I compress your video with traditional video compression algorithm, right, like linear interpolation, will it work to a certain extent?
Yeah, so in our experiments, so we also show that our universal adversarial perturbations can be transferable to conventional video codecs and have a higher attack success rate than the Gaussian random noise.
Thank you.
Thank you for the great talk. So I have a question. So we all know that adverse text or universal perturbations can break those deep learning models. So what's the specific challenges in your video compression tasks?
The specific challenges are so our attack can have some margin to be improved in the future work because we assume so many. So our adversary has no prior knowledge about GOT structure, encoding parameters, but if adversary can extract good information from the streaming video, so adversary attack can be further improved.
Thank you.
So the last thing you said, so you said that the attacker can infer information about the compression model from the stream video. Is that correct?
This can be the future work.
Okay, I see. Because I was trying to think of like the correct model here again, like what scenario would allow the attacker to feed the perturbed video to the compression system?
Yeah, I'm sorry for giving the condition. We have no assumption about our online attack, so we minimize our threat model. We minimize our assumption in our online attack threat model.
Okay, I see.